Welcome to another episode of ZCash Simplified. Last time we talked about shielded transactions in general on ZCash and Merkle tree overview. And today let's talk about the intuition of zero knowledge. Because, as I said in the last time, I want to have this whole explanation in a way that anyone who has no prior knowledge about any of that can get an understanding of it. I call it this time from zero knowledge to zero knowledge. As always, disclaimers, this is my own research, expected mistakes, don't take anything for granted here. This is of course not financial advice and everything. If you want to know more about the motivation why I'm doing this, the background or anything, watch the first video. Today I don't want to spend any time on that, and let's get right into it. So, zero knowledge proof. What's a zero knowledge proof? The intuition about it is that you want to prove that you know something without revealing the secret. So I want to, you don't want to share anything about the secret so that the other one doesn't know the thing, but you want to convince someone else that you know it. And usually you do that by producing an outcome that is only possible if you know the secret. A very, very simple intuition from real world would be, for example, that you have a car and I want to prove to you that I have a faster means of transportation than your car. But I don't want to tell you what it is. I don't want to show you anything about it. Nothing. I just want to prove to you that I can be faster than you with your car. And we could do that by meeting at one place, agreeing on a target. You get into your car and start driving, and I meet you at the target before you are there. So I reach the target before you are there. So when you reach the target, I'm already there waiting. With that, I would have proven to you that I am faster than you with your car, but you have no idea how I did it. So it's a zero knowledge proof, so to speak. But in our context of blockchain, that's not really applicable because there are no cars on the blockchain and nothing like that. But still, there is, we want to have a zero proof, zero knowledge proof, and let's do a first intuition without math. There will be math today. Don't worry, it will be not too much math, but we are getting into the areas where math is needed. But let's first get a bit less rough, but still rough intuition on zero knowledge proof without math, still a bit of real world. Let's say you want to prove that you can see color to a blind person. So you have two objects that feel exactly the same. So for the blind person, those two objects are exactly the same, but they have different color. You see the different color, so you can distinguish those two objects, but the blind person can't. The blind person has no idea how you should be able to distinguish them. How do you prove to the blind person that you can distinguish the objects? One option would be there that you tell them to take the objects and switch them behind their back. Or you leave the room and they switch it, or some way of they switching it without you knowing if they switched or not. They decide randomly if they switch it or not and show you the objects again. And now if you really see the color, you must be able to tell if they switched or not. So if you say the one in your right hand is right now the red one and the one in your left hand is the blue one, and then they switch or not, you must be able to tell them where the red one is, or if they switched or whatever. If you are not able to do that, you can't. The proof failed. If you are able to do that, you still would have the chance to guess, right? So it's still not a proof with one thing. So you play a bit of an interactive game by saying, do it again and again and again. All the time, they randomly choose if they want to switch it or not, show you the two objects, and you always have to correctly point out which one is the red one, did they switch or not. And if you can tell that every time, if every time they do it, you can correctly point out which is the red one, which one did they swap or not, the probability that you are faking it, that you are guessing, goes to 0. Because if you're wrong once, the proof failed. You have to be right every time, and that's nearly impossible. If you do that 10 times, 20 times, it's nearly impossible to guess that correctly. So you've proven that you can distinguish the two objects, but the blind person has no idea how you do it. You don't even need to tell them that you see color. You can just tell them, I am able to distinguish those two objects. And they won't ever understand how you do it because they have no idea of that. So that's a bit of already going closer to where we will go with the math now. So that's why I'm doing this first without the math. So keep that in mind. This interactive game of they choose randomly if they swap or not, and you have to then prove to them based on their decision. So that's the without the math. Now let's get into the real stuff with the math. This is still only intuition today, right? This is not how zero-knowledge proofs directly work in ZCash, because there's more complex math that we will go into in the next videos. Today it's just about getting an idea of how this whole thing works already on a math basis. So for that, we now assume that we live in a world where multiplying and therefore squaring numbers is easy, and you can do that. So you can calculate a times a for any number a, and you get a squared. But let's assume in this video that it's impossible to calculate the square root of a value. So you cannot invert a squared. If you have a number, you cannot find out if that's a square of another number or what the square root of it is. That's our given now. So we need to assume that this is the case. Now we say, okay, Igwit, so first player, so to speak, Igwit knows a secret S, and she publishes big V, which is S squared, as kind of a public data. Because there's always some public data that you prove against, so to speak. So this V is publicly available. And now Igwit wants to prove to John, who knows nothing, that she knows S without revealing S. So she needs to show John that she knows the secret, but without telling John the secret. How could one do that? Again, with something similar to what we had before, an interactive game. Igwit knows the secret, and first she chooses a random number, calculates the square of this random number, and sends this square from the random number to John, which is, we call it the commitment, because she does that at the beginning of each, we will see this will be multiple iterations of that, and at the beginning of each of the iterations, she commits to this random start, so to speak. She already before kind of committed to the secret, but she knows the secret, so that's not really a commitment. And here she commits to this random number. Now John can just say, he says, like before, the blind person who decides to switch or not, John now randomly chooses true or false and sends this challenge to Igwit. So he now gives her the challenge. This is true to that or false to the other thing. If John says true, Igwit needs to calculate her random number from the beginning times her secret and sends that to John. John can now verify that the square of what she just sent, the y, equals x times v. So original commitment times v. And don't worry, this is the maximum of math that we see today. So just get through that. This checks out because, so if everything is correct, Igwit sends the correct S, sends the correct one, has the correct random number and everything. Then this checks out because y squared is random number times s squared, which is random number squared times s squared, and this is x from the original commitment times v, which is s squared. So John can verify that, and if this is verified, he says this proof is valid. If John says false in the challenge, Ingrid just reveals her random number. And now John can verify that y squared is x, so that this random number is actually what was used in the commitment. Now, first question, does this prove that she knows the secret? Second question, is it zero knowledge? Is John getting any knowledge from that? First, does it prove anything? And basically, the question if it proves anything is about, can she cheat? And so let's look at this whole thing is if she already knows what he will do or correctly guesses true or false, she could prepare an answer. So let's look at it. If she guesses the correct challenge, for example, she guesses false and John actually says false. If she guesses false, so she sends a random commitment, he says false, she just has to reveal the random number, everything's good. Because he said false, she just needs to reveal the number, proof confirmed. She guesses correctly. If she guesses correctly true, so she guesses true and John says true, when we look back at this, if she guesses true, she needs to send something so that this checks out. She can send something to this so that this checks out if the original commitment is random. So she needs to now send a commitment in the beginning, assuming that he will say true, which fulfills this stuff. And for that, she just sends v as the original commitment, the x, because if she can then send y equals v again, and now y squared is just x times v, because x is v and everything is v. Basically, v squared is v times v. So this again checks out for John, and she got away with it, so to speak, if she guessed correctly. But if she guesses wrongly, she guesses false, so she sends just a random number squared. He says true, and now she would need to send a y such that y squared is x times v. But x times v is x times s squared, and there is no way of calculating a square root of something. And this is a random number that she just committed to. So she cannot find a y if she doesn't know s. So assume that she doesn't know s, she's just guessing. So she can't find a y so that this is valid. So she can't send the correct y, and the proof failed. Same thing if she guesses true in the beginning. Because if she guesses true, she needs to send that so that it all checks out. She sends x is y, x is v. John says false. It doesn't say true, he says false. And now she has a problem that she needs to find a y so that y squared is x. But she just sent v, and she doesn't know the square root of v, because that's s, which she doesn't know. And so she doesn't know what to send so to fulfill that, so she can't send that, and the proof failed again. So if she guesses, she has a 50-50 chance of guessing correctly, and therefore if she guesses correctly, it's all good, but if she guesses wrongly, she has no way of fulfilling that. So there's a 50% chance of faking the proof in one iteration. Now, same as before in the iterative game, to iterate it multiple times, since we're on a blockchain in the computer science, you can iterate easily multiple times. So let's iterate 40 times, and that gets the probability of she faking the proof and guessing correctly every time to 0.00001%, so practically zero. One important thing to note is, and that's important for the zero knowledge proof, property that we will check next. Yes, we iterate here, but in this iteration, as I said before, this commitment in the beginning, where she chooses a random number, needs to be a new random number every time, of course. But we will see y. So next step, is it really zero knowledge? Zero knowledge means she proves it without revealing any information about her secret. So there must be no way of John to extract any knowledge about this. Now, John only knows V. He can't invert that because we said that's not impossible to invert, to calculate the square root, so he doesn't know S in the beginning. And now doing the calculation, if you look at it, depending on what he says, at the beginning he gets a random number squared, which is for him a random number. He doesn't know anything. That gives you no information about S, right? About the secret. If she says true, he gets the secret sent in some messed up form, but for him it's a random number times the secret, and he doesn't know the random number because he can't get the random number from the commitment, and he doesn't know anything about this. So he cannot get any information out of that. He could start guessing around and try to guess an R so that he gets the X, but since it's impossible to calculate that, it's a guessing game, right? He can also start guessing S directly and would have the same chances. And that's basically what this whole thing is about. You might hear in future videos or in other papers or anything that it's zero knowledge if an attacker would get the same information or probabilistically significantly the same information from a random simulator as if he does the proof review. So John gets the same information from her proving that she knows that as if he just starts a random simulator and tries to get a random S. And that's what's happening here, because he gets just a random number. He gets no more information about this than by just randomly guessing numbers. In the case of he says true, and in the case where he says false, he just gets the random number revealed. So there's no way of any extraction of information about S. Anyway, as I said before, very important that Egrid always chooses a new random number, and those need to be real strong random numbers. Because if you do it 40 times and you always use the same random number, it's if he says false, he gets the random number revealed. Now he knows the random number. If she chooses the same random number in the next iteration and he just says true, suddenly he knows the secret. So that's important from her side that she sticks to that. But if this happens, we have exactly this. He only gets a random number squared and the random number times the secret. And since he can't invert that, and y is just a random number, and he can never extract S from the conversation. And with always a new random number, all he sees is random numbers, and there's no way of extracting any knowledge about that. So yes, it proves that she knows the secret, and it is zero knowledge. This is all nice, but if we now look back to our from last video, what we want to prove, what the zero knowledge proofs in ZCash proves, this is not about knowing one secret. This is about calculations, about properties, and about relations of numbers to each other. There's far more complex things in there, and we will come to that in later videos. But if you just look at that, there's a simple calculation in there. And if we want to prove that via zero knowledge without revealing the values, that's different than what we just did here with proving that you know a secret. So let's quickly look into that. We will not prove exactly this calculation we had there, because therefore we need different math, but something similar so you get the idea. So from secrets to calculation. What if Egrid doesn't just want to prove that she knows a secret, but that some secret input that she used correctly fulfill a calculation with a public output? That's again an important thing. As I said before, you always have some public data that you prove against, so to speak. So your target to prove. Because there needs to be some publicly information that verifies your proof. Because it's not possible to say, I prove to you that I know this, and there is no way that this leads to any result that have anything to do with you and you know nothing about anything, because then there is no reference in the real world that gives you any clue if I'm right or wrong, right? So there needs to be some public information, some public data that you can prove against, so to speak. So there is some public output of the calculation. In our case here, just to have this real world thing, you could on the one hand say there is no publicly known output, but you could change that calculation that you say it's not VA plus VB is VC plus VD, but you could say VA plus VB minus VC minus VD equals 0. It's the same thing, right? So they need to be the same. So the one minus the other is 0. And suddenly you have 0 as a publicly known output that you say, okay, I have 4 numbers here, and this calculation of those 4 numbers lead to 0. And I want to prove that. So you have your public output there too. So for us in our system, since we do squaring and we have again the same thing where square root, we stay in a simple system, square root is impossible, but multiplication is easily doable. So we use a multiplication calculation and we say, okay, eGrid has inputs, secret inputs A and B, and wants to prove to John that A times B equals C, with C being the public data. And she doesn't want to reveal what A or B is. She wants to just prove that A times B is C. Now, this time it's a bit more complex than the first thing, but not much. First, eGrid calculates, so to speak, a bit more commitments. She calculates uppercase A, which is just small a squared, and uppercase B, which is just small b squared. And she can show that to John, because since square root is not possible, he will not get any information from A or big B to her secrets. But with A and B, John, so the uppercase A and B, John can verify that uppercase A times uppercase B is C squared. Because he knows C, so he can calculate C squared. And he can multiply A times B. And if this is true, it must mean if A and B are actually squares of the numbers, this would mean that A times B is C. John still doesn't know anything about A or B, just that if A and B are squares, that this calculation is true. But so far, eGrid could still cheat by just guessing any B, take an A that is C squared divided by big B without actually having A and B and having it fixed. So without knowing the real small a and small b, but just faking that. She would send this is a proof, I have numbers, and if he just checks that, it wouldn't help. But we have already a process, a zero-knowledge way of proving that for a public big A, she knows the square root of it and it's fixed, right? And that's exactly what we have here, because for a public number V, you know the square root. That's what we're proving here. And now we have these 2 times. We have the public big A and public big B, and we have the small a and small b, that's the secrets. And so we do the same interaction as above, once for secret lowercase a and public data big A, and once for this secret B and the public data big B. And since she commits to them, she sends uppercase A and B to John in the beginning, and then they do this interactive thing. It's locked in from the start, so she can't change that on the way or something. So she proves that she knows the A and the B, so that big A and big B are valid, and John can verify that A times B is C squared. And together with those proofs, now everything is proven, that those things hold and the calculation holds, and eGrid just proved to John that there is a lowercase a and lowercase b that she knows and she committed to, that fulfill this calculation without ever revealing any information about those two, any other information except that they fulfill this calculation, but any more detail. John knows nothing more about that. So we now have a way to prove, zero-knowledge prove a calculation, not only knowing a secret, but also that those secret values fulfill a calculation with a public output. Now, what to do with that? It's already, I already said that, but just as a quick sum up, the idea what to do with such a zero-knowledge proof and zero-knowledge system is that we can prove the correctness of a calculation and or that you know a secret without exposing the secret inputs of the calculation or your secret. And as I said before, that's basically exactly what you want to do in a shielded transaction in ZCash, because we have secret inputs, secret values, we have secret inputs of the who sent stuff, what amount is sent, where is it sent to. That's all secret input, and there are public outputs, like the Merkle tree root is a public output. The commitments are public outputs, kind of. Nullifier is a public output because they are there. And so we have public data and we have secret data, and we want to prove that we choose a secret data that verifies or that fulfills defined calculations leading to those outputs. And that's exactly what we are going to do with zero-knowledge proofs. As I said before, squaring, this is not exactly how ZCash does it. We will come to the actual ZCash math in the next videos, but this already gives you a bit of an idea how such math can look and what it will be like. And it will be similar to what we have here, but different. So stay tuned. I hope this was not too much math, but I hope it gave you some idea and insights how zero-knowledge can actually work. With that, if there are questions, leave a comment. Otherwise, see you in the next video.